Right, on today's stream, we're going to be looking at the normal reaction force. So we've got book of mass, nice easy question, hopefully to start off with, maybe not, but we'll find out. Mass 0.6 kilograms, rests on a horizontal table. Child pushes down with force 12 newtons. Find the magnitude of the normal reaction. I'll give you 2 minutes to start off with. We'll see how my class gets on with it. If we find it too easy, we can finish early. Okay, so let's draw a little diagram. Always draw a diagram. Oops, wrong one. I didn't do that. Always draw a diagram of your question. Yeah. Shapes. So here we go. We've got a box, and that's going to rest on a horizontal table. So just draw a table. Move it up slightly. There we go. So we've got a box on a horizontal table, and it has mass 0.6 kilograms, so its weight will be 0.6 g. A child pushes down with force of 12 newtons. Find the magnitude of the normal reaction. So the normal reaction will be going this way. Now, unless it falls through the table, we must be in equilibrium. So that means the normal reaction will resolve. Always good habit to say which way you're resolving. We resolve vertically, so R will equal 12 plus 0.6 g. And if you use g as 9.8, that comes out to be 17.9 newtons to 3 SF. Okay, next question. Question 2. We're going to take another 2 minutes to have a go at this one. Okay, so here's our box resting on our table. So box 15 kilograms. So 15G is the force going down there. And it's attached to a vertical cable that can be modeled like an inextensible string. So it will have a tension. And we got the normal reaction between the force and the ground is 68 newtons. And we want to find the tension in the cable. So we're in equilibrium because it's not moving anywhere. So therefore, if we resolve vertically, we have the tension plus the 68 newtons must equal 15G. So T will equal 15 times 9.8 minus 68, and that comes out to be 79 newtons. Right, moving on to question 3. Another 2-minuter. Let's have a go. They're going to get slightly harder now. We're going on to lifts. Okay, so that's 2 minutes up. Let's just draw a quick diagram of this. So we've got a crate of mass 120 kilograms lying on the floor of the lift. The lift accelerates upwards at 0.4 meters per second squared. Find the magnitude of the normal reaction force between the crate and the floor of the lift. So we now have a resultant force. Okay, it's not an equilibrium, it's accelerated. We have a resultant force which must be causing it to accelerate upwards. So that must be equal to the forces in the same direction, R, minus the forces in the opposite direction, mg. And the resultant force we know is equal to ma. So ma equals R minus mg. So let's put our values in. So we got 120 times 0.4 equals the normal reaction, which we don't know, minus 120 times 9.8. Therefore, R will equal, we can add the 0.4 to the 9.8 to get 10.2 times 120, which gives us, when we calculate this, I'm just looking at my answers, 1,224 newtons. Right, next question, question 4. And I think I'm going to give you 5 minutes for this. You might finish early. I'll see how the class go with me. I might just call it early. We'll see how we go. Right, we'll give you down to 1 minute because most of my class have finished already.
One minute to go.
Okay, that's the 1 minute up. So let's draw a diagram. So here's our diagram, and unfortunately, I didn't leave myself in a space, made it too big. Okay, so we've got the 500G here. Grab that and bring it back up here. So we got the person, they got a normal reaction with the floor, they have a weight of 35G, and as the weight of the lift is 500G, and a tension acting up here. So when working on the tension in the cable, we're going to just look at the external forces, the tension and the two massive weights acting together. We know that it's accelerating upwards with 0.6 meters per second squared. So the resultant force on the external forces will be equal to the tension minus the two masses, okay, the mg of the lift and the person. So the resultant force equals ma, and m in this case is going to be 535, which is the lift and the man, or child in this case, sorry, times by 0.6 for the acceleration. We don't know the tension. We know the mass, 535 times 9.8. So the tension will equal 535 times, add the 0.6 into 9.8 will give me the 10.4, and that comes out to be 5564 newtons. Looking at the magnitude of the normal reaction between the child's feet and the floor and the lift. So we're now just going to look at the forces acting on the child only to resolve vertically on the child. Okay, so again, we're going to be accelerating, so the resultant force will equal the mass times acceleration, but the mass is now 35, and the acceleration is still 0.6 meters per second, and this is going to be the resultant force going up minus the 35g going down, and g is 9.8. So therefore, the resultant force will equal 35 times 10.4 as well, and that comes out to be 364 newtons. Right, next question, question 5. Give you 3 minutes for this one. You should be getting the hang of these. Off you go. Okay, so okay, my diagrams come out a bit big again. It's cheating a little bit, isn't it? Just pasting it in. I'm just going to just view that down a bit. There we go, so we can see it all. Right, so we've got our person who has mass 85 kilograms, so that's 85 g on the weight, and the lift is 360 g for the weight on that. It's got suspended by an inextensible cable, and that has a tension T. The person will have a normal reaction between them and the floor of the lift, and we know that it's moving downwards and it's deaccelerating. So that means acceleration, if it's moving downwards and its deacceleration, is up at 4.2 meters per second squared. So our resultant force will equal, because it's accelerating upwards, it's going to be equal to the tension minus the total weight of the whole lift. Okay, so that's going to give me minus. Sorry, I'm looking at the wrong thing. Sorry, apologies. I'm reading the wrong question. Moving downwards and deaccelerated 4.8. Just change that. So I've got my resultant force 4.2. That's okay. No, my resultant force is going to be equal to what we're trying to do. I haven't read it. Find the magnitude of the normal reaction. Sorry, I was reading the wrong question. Find the normal reaction here. So we're going to have R minus the 85G here. So the resultant force will equal to the 85 times by the 4.2, the mass times acceleration, and R minus 85G. So therefore R will equal 85, add this onto 9.8, so that will give me times by 14. So therefore R will equal 1190 newtons. Apologies, I was reading the wrong question on the start of that. So part B, moving upwards at constant speed, that means acceleration is equal to 0. So that means we're in equilibrium. So that means all the forces going up equal all the forces going down. So therefore R will equal the 85G. That will come out to be 833 newtons. Right. Yep. It depends. You can do it both ways. What I've done is I've taken that the resultant force must be going upwards. So therefore, because I've taken my resultant force as going upwards, I've made my acceleration positive. So I've decided my positive direction is upwards, even though the velocity is downwards. I didn't decide to make my positive direction the same as my velocity. So my positive direction was my MA, and therefore I'm going to have that as my resultant minus the force in the opposite direction. So what your resultant force must always equal, it must always equal the forces in the same direction minus the forces in the opposite direction. Does that answer that question? Okay, cool. Right, question 6. I'll try and just move it slightly so you can see it more easily. Okay, there we go. And we're going to give you for question 6. Let me look. I had timetabled 5 minutes. We'll see how you go.
1 minute to go.